All right, let's get started. So today we're talking about HTTPS. But first, so we're going to talk about HTTPS. We're finally going to get encryption in our web apps. Last time we talked about encryption itself and how to encrypt, and we talked about public key encryption systems. I have to make some errata here. I made a mistake. I misspoke last time. Elliptic curve encryption is not safe from Shor's algorithm. Those will fall as well. I was under the impression that those were immune to quantum computing. That's not true. I looked it up after. I'm like, I got to study this up and get brushed up on this again. They're not. Not at all. There is a variation of elliptic key encryption that might be, but there's debate about it right now that they're not quite sure. Not quite sure if it actually is post-quantum is the term. Not quite sure if it's a post-quantum algorithm quite yet. So we might be in more trouble than I thought if quantum computers just suddenly have a big advance in functionality and usability. So with that, any questions before we talk about HTTPS? Then let's talk about it. First, we want to talk about certificates. Oh, I forgot to look up my keyboard shortcut. Oh, well. It might be a little hard to read some of my demo for this. So we want to talk about certificates. So we talked about public key encryption last time. Today, we want to talk about certificates to start and all the things that go into HTTPS, which is a decent amount. There's quite a bit involved with it. So we have this problem right here. So we have public key encryption, and I said you generate your public-private key pair, and this is in the context now that we're outside of just encryption and into where we want to start talking about encryption on the web. The way this works is your web server will generate a public-private key pair, keep the private key private, of course, and then the public key it sends out to everybody who asks for it. Anybody who wants your public key for your server gets that public key, and then when somebody wants to encrypt something and send it to you, they encrypt it with your public key and send it to you, and you decrypt it with the private key. That's how it could work. That's how it could work in theory. Of course, it won't if I'm saying it like that. So we have this one attack. This one's a pretty bad one, this man-in-the-middle attack. So you want to connect to a website. You say, yo, web server, what's your public key? Web server responds with their public key, and instead of you getting their public key, there's somebody intercepting that traffic, takes that public key, throws it away, and then replaces it with their public key and sends their public key to me. Now, when I'm talking to the server, I have what I think is that server's public key, but it's not. It's somebody else's. Somebody else got their public key in my hands and made me think that it's that server's public key. So now when I'm encrypting things to the server, I'm actually encrypting it using their public key, and it's using the attacker's public key. The attacker's going to get all the messages that I send, decrypt, read it, and do whatever malicious stuff they're going to do. The first thing when you visit a site, one of the first things you're going to do is type in your email and password. They get your email password, decrypt it, and then they're gone. And then they can connect you can connect back to the regular site. You have to refresh, and you're just going, oh man, that was weird. And then everything works after the refresh. But the attacker, meanwhile, got your password, has your credentials, and they can attack you at their leisure after that. This is a pretty bad attack. We need to address this. It has to be something done, and this is where certificates and certificate authorities come into play. So a certificate authority is going to issue certificates. And those certificates, a certificate is a public key with some extra information. So a certificate authority is an authority that is going to issue certificates. And we assume, this is where things get maybe a little uneasy. It works, for the most part. But all of encryption, all of security has to start with some assumption of security. There has to be some communication. The first communication, you have to just assume that it's secure. One way or another, that has to happen. For our purposes on the internet, we're going to get a certificate authority's public key pre-installed on our machine, either with our operating system or a browser. We're going to have these public keys of these certificate authorities installed on our machine, and we're going to assume that nothing went wrong with that process. If someone can interfere with that process and get their public key installed on your machine as a certificate authority key, then everything blows up and you're not safe on the internet anymore. So we're going to assume that that went well with this installation process. And there are extra steps you can take to make sure that goes well if you're really paranoid, if you really want to double check this. And then the certificate authority is going to issue certificates for your domain name. They're only going to issue certificates for domain names, not IP addresses, domain names, and subdomains if you want to go that route, if you want to set up subdomains with separate certificates. So what you do when you want your certificate is you talk to the certificate authority. You say, hey, certificate authority, I am who I say I am. I do control this domain name. And they'll verify that you do actually, in fact, control that domain name. And when you do, they take your public key and they turn it into a certificate. I say turn it into, but this certificate is going to contain your actual public key, the domain name, and the certificate authority that signed I gave it away. But that issued the certificate, the domain name it's for, certificate's for a specific domain name, and then a cryptographic signature of a hash of the certificate body. So everything about the certificate, all the information, all the contents of it can be out in plain text. But then the contents of it are going to be hashed. So you can take the contents and hash it and verify this. You hash the certificate, and then the CA will cryptographically sign that certificate with their private key. Now you can verify that signature. You see the CA name, you pull up the public key for that CA, and you verify the signature, get the hash, and then hash the contents of the certificate and make sure the hashes match to make sure that that is a valid certificate. So if that signature verifies, if everything goes well with that, then you can say, yes, this certificate was in fact issued by that certificate authority. So you can verify that the certificate was issued by the CA, which gives you confidence that this public key does in fact belong to this domain because it was verified and signed by that certificate authority. So this is how we distribute public keys on the internet. We never just send raw public keys. We send certificates that have been signed by certificate authorities. And that's what's keeping us safe in there. So our man-in-the-middle attack, they can't verify that CA signature because they don't have the CA's private key. And if you're running a CA, you're doing everything in your power to keep your private key private. That's your business, depends on it. So those private keys are going to be secured. We hope, at least. I mean, things happen, and they make headlines. But we hope that those CAs keep their private keys private because all encryption on the internet depends on it, or else we're open up to these man-in-the-middle attacks. I guess not all of it. Everything doesn't completely crumble down. But anybody capable of executing this attack is going to have a lot of power, a lot of access. But that's not 100% how it works. When I said CA certificates, CA public keys, they are actually certificates. But the CA certificates and public keys that are installed on your machine actually aren't the certificates for every single CA. They're certificates for what we call root CAs. So you'll have a handful, I say a handful, but I don't know, 100 or so, root CA certificates installed on your machine. And every certificate that's issued on the internet must be able to be verified by one of those root CAs but there are many, many, many more CAs than just the root CAs. So what we do is generate things called key chains that have to end in a root CA. So instead of having your certificate signed by a root CA, you'll have your certificate signed by a certificate authority, a CA, just a regular CA, and then that CA might have their certificate signed by another CA, which could have their certificate signed by another CA. You can have as many links as you want in this chain, as long as the very last one, that last CA, has their certificate signed by a root CA. So as long as this keychain from the domain you're visiting, their certificate can be verified all the way up to, through the keychain, to a root CA, then you can say that that's a valid certificate. And usually whenever I check these, the chain is two. You have the certificate for the domain signed by CA, which is signed by a root CA. In practice, that's what I've been observing, is just one step in this chain. But the chain can be as long as it needs to be. If you have a certificate that can't be verified by a root CA, you have what's called a self-signed certificate. Even if it is signed by CA, if that keychain doesn't end in a root CA, that's a self-signed certificate, and it shouldn't be trusted, except in development purposes, as you'll do for homework 4. You'll have self-signed certificates, and you're going to trust your own stuff, of course. But you shouldn't be trusting self-signed certificates anywhere. That's where you get all the warnings in your browser. Your browser will say, hey, this site is not secure. That means something's wrong with the certificate. Either it doesn't exist, or it's a self-signed certificate, or it's a valid certificate that has expired. Is pretty common. If even major sites, every once in a while, they'll have a certificate expire and not have the new one to replace it right away, and they'll have a little bit of downtime. It happens even time to time. Major websites have that problem. Somebody just messed up the process of all that. And that's how we're going to be safe on the internet. So to look at a certificate, you'll go to this lock icon. It says connection is secure. It'll be a little different in every browser. And this is, I forgot to look up the shortcut for my magnifying glass and to make this bigger. But what we can see is that my certificate for cc312.com was signed by this R3, which I thought it had a longer name than that, which is not a root certificate authority, but that was signed by ISRG root X1, which is a root certificate authority with a certificate that's signed, not signed, but that's verified on my machine. And if I look at, I forget in this browser how to even do it. Let me try. No, I know how to get there. Give this a brief shot. There we go. So I can look on my device and see all of the root certificates. Maybe I can just zoom in on this. I can see all my root certificates. So there's quite a few, but not an absolutely tremendous number of root certificates that are installed. And if I look through this list, I forgot what it was, but it's too small for all of you to see anyway. But if I look through this list, I can see that certificate that was the root certificate that signed the CA certificate that signed my certificate for cc312.com, but I won't see that intermediate CA, the one that had to get their certificate signed by the root CA. That won't be in this list, but all the root CAs will be. And these are the only certificates that you can trust on the internet, anything that's in this list. But on the other hand, if an attacker can spoof any one of these certificates, they can have fake certificates for websites that they don't control that will still show that lock icon in your browser. Your browser will just happily take you there, even though you're talking to an attacker. So every one of these has to be secure. Okay, so that's certificates. What does this have to do with HTTPS? Well, hopefully you can see everything. It has everything to do with it. HTTPS, commonly called HTTP Secure or Secure HTTP, what it actually is HTTP over TLS. That's what the actual HTTPS really is, and let's explain what that is. So SSL or TLS, if you see either one of these acronyms, this is one thing that somebody decided just to confuse us, that they're going to change the name of SSL to TLS. So if you see either one of these, they mean the same thing. It's the same thing. But once SSL was going to come out with version 3.0, we have SSL 1, SSL 2. Once they were going to do SSL 3.0, they renamed it to TLS 1.0. So they just switched the name of it. And some libraries, including the one we'll use to generate certificates, it's still called OpenSSL. OpenSSL actually implements TLS these days, but they're not going to change the name of the library to reflect the name of the protocol name change. I don't know why they change protocol names like that. Secure socket layer rolled off the tongue so much too. Transport layer security, I suppose, is more accurate, but I don't know. Did they have to change the name? But anyway, SSL, TLS, they're interchangeable. If somebody actually is implementing SSL, they're not secure though. SSL is outdated. Nobody should actually be using SSL. Use TLS. Even TLS 1.0, I believe, is insecure at this point. A lot of web technology, routers don't speak TLS. Web servers, browsers, refuse to speak TLS 1.0 or any SSL version. I believe TLS 1.1 is the oldest one that is widely used and accepted still. I might be a little bit off on that, but I believe that's the case. So if we open up our network stack, this is how our network stack looked. We have our IP at the, I don't remember the layer names. I'm sure some of y'all do. Take Modern Networking Concepts if you want to see the network stack in depth. But we have our transport layer, TCP, and our application layer, HTTP. TLS is going to go right in between TCP and HTTP. So TCP is going to work just the way it always has, except by the time we get to TCP, our data is going to be encrypted. So TLS is going to encrypt everything above it on the stack. So HTTP, WebSockets, anything that we're sending and receiving is going to be encrypted. But when it's being sent, the TCP and IP layers are not encrypted because TLS is sitting right in between HTTP and TCP. Briefly mentioned this last time, but your TCP and IP headers are not encrypted. And this is why they're not low enough, or they're not high enough, rather, in abstraction on the network stack, because TLS is right here. But our HTTP remains the same. It just means that our HTTP stuff is going to be encrypted and then sent over the TCP socket. So once we send something on the TCP socket, encrypt it, and then send it, instead of just sending it. Other than that, other than how we interact with TCP, HTTPS is the exact same protocol as HTTP. So we're doing this, I mentioned this a few times, but we're doing this through Nginx, and Nginx is doing our encryption on the other end. And then from Nginx to our app is unencrypted. But even if we did encrypt with our app, it only affects the way that we communicate over the socket. And it's something we could do. Maybe I'll demo it next week, I guess. I guess I could do that, actually. We can install the certificate into our TLS socket server and then just use the socket server as we always have been. It's a few extra lines in your main method as you're spinning up the socket server. And then you'll have HTTPS in your app. Nothing else has to change. Nothing in receive changes at all. You still call the receive method as you always have. Everything's exactly the same. But when you send or receive data, it just happens to be encrypted before it's sent. That's the only difference. So we got to add this TLS layer. I really hammered that slide before I got to it. So how do we use TLS? So let's talk about TLS in a bubble, just what is TLS itself. So this is going to give us a way to do two-way encrypted traffic. So when we send things to a server, we want it encrypted. When we receive things from the server, we want that to be encrypted. Okay, sending things to the server, easy enough. Get the certificate, verify that has been signed, has a keychain that leads to a root CA. I verify that is the public key for the domain I'm communicating with. I have my message I want to send. I encrypt it with the public key, fire it off to the server. That's encrypted. The server can decrypt with their private key. Done. Now the server wants to send me a message. Oh, shit. What do? We don't have any mechanisms in place for that. We could have users generate public-private key pairs. We would like our users to send their public keys to CAs and get them signed so the server knows they're actually talking to us. We could do all that, but we don't. It's not how we do things. We're going to do things like this. So we're going to have a TLS handshake where we're going to agree on a symmetric encryption key. So we're going to need a new crypto system for our communication called a symmetric key encryption system as opposed to a public key encryption system like we saw last time. Symmetric key means that our messages are encrypted and decrypted with the same key. So client and server need to agree on a key, and then they'll both use the same key for encryption for that connection. So how are we going to do that? So we have to do this. We have to agree on a symmetric encryption key, to the point where even if somebody's listening to everything, even if we have a man-in-the-middle attack, no matter what, we need it to still be secure and agree on that symmetric key without anybody else being able to get that symmetric key. Sounds tricky, but the Diffie-Hellman Key Exchange is going to do this for us. This is another case where there are lots of solutions to this. This is just one of them. I think this is one of the simpler ones to understand, so it's fun for lecture because we can go through the whole thing. Pretty much the whole thing is on screen right now. And it'll give us an algorithm to be able to compute symmetric keys. So the way we do this is client and server will agree on two values, P and G, where G is a generator for the group P, and P is a prime. So P is going to be a large prime, and G is going to be a generator, which means I don't want to get too lost in the woods on this one. This is all abstract algebra stuff. If you ever take that, if any of you are going to take that math class or have taken it. G is a value such that if you keep multiplying G by itself, so G to any power 1 to P minus 1, if you raise G to all those powers, you'll end up getting all of the values from 1 to P minus 1 without repeating any values. So this is called a generator because as you keep multiplying G by itself, you're going to run through all of the different values that can be generated in the group P, which is all the values, I forgot to mention mod P. All that's mod P, which are all the values that you can get when you take a value mod P, except 0. If you're multiplying, you're never going to get 0 unless G itself is 0, and 0 is not a generator of any group because no matter how many times you multiply it, you're only going to get one member of the group, not all P minus 2 members of the group. So G is a generator. If you keep multiplying G by itself, it'll cycle through mod P. It'll cycle through all the values 1 to P minus 1 in some crazy order. There will be a lot of properties to that order. It won't be 1, 2, 3, 4, obviously, but that's what we want. G and P, where G generates the group P, and P is prime. These are public values. Everybody gets to know these. Everybody on the planet can know P and G. Then client and server will both come up with a random number. All on their own, client's going to come up with some random number A. Server comes up with some random number B. And these are private forever. To the point that the client's value A won't even be known to the server, and the server's private number B will not even be known to the client. Nobody gets to know these values. They don't even share these values with each other. They're private forever. Nobody gets to know these values except the person who generated them, or the code that generated them, more accurately. Client is going to compute G raised to the A mod P. And this is where it's important for G to be a generator. We want to take advantage of the entire group P. If G is not a generator, we're not going to get the full value of P, because if G generates like half of the group P, we're going to, well, I'm getting lost in the weeds on that one. We don't need that. If anybody wants that explanation, I'll be happy to. So the client is going to compute G to the A mod P, send that value to the server. The server is going to take this value, G to the A mod P, and raise it to the value of B mod P to generate this value, G to the AB mod P. On the other side, the same thing is going to happen, just in the opposite order. Server is going to compute G to the B mod P, send that to the client. Client raises that value to the value of A mod P, so they're going to have the value G to the AB mod P. Since multiplication is commutative, it doesn't matter which order these are computed in. The server is going to raise it to the B to B. The client's going to get a value raised to B and then raise it to A. The server does it in the opposite order. But it doesn't matter. They're both going to arrive at the same value. So now server and client both agreed on this secret G to the AB mod P. And they can use that either just straight up as their symmetric encryption key, or throw that in some function which is going to give it whatever properties they need for whatever crypto system they're using to be able to use that as an encryption key, as a symmetric encryption key. So we agreed on a secret, G to the AB mod P. We have a shared secret between server and client. Everybody knows G, everybody knows P, they're both public. A and B are both super private, even the client and server can't know each other's values. And the only values that went over the air, or over the network, over the wires, and air and the Wi-Fi, are G to the A mod P, G to the B mod P. These are the only values that everybody gets to see. So if I'm an attacker trying to attack this key exchange, I have G, I have P, I have G to the A mod P, I have G to the B mod P. My task as an attacker is to take the discrete log base G of either one of these values, or both of them. I guess you'd have to break both of them. No, you'd only have to break one of them. Of one of those two values, you have to compute the discrete log. And as we saw last time, discrete log, as it turns out, is a really hard problem to solve, thankfully. This is one of our cryptographic primitives. So this key exchange does reduce down to a cryptographic primitive. Breaking Diffie-Hellman implies that you've broken discrete log, that you can compute that efficiently, which is generally agreed to be a very hard thing to do. Maybe someday possible. It's not proven to be hard, but it's pretty well agreed upon to the fact where a lot of cryptography depends on that being hard. So we have quite a bit of faith that it's a hard problem, that and factoring primes. And then we use that shared key for a symmetric key encryption system. AES is a good choice for that. There was DES, which is pretty well debunked now. It's pretty well, there are too many attacks, too many vulnerabilities. AES came along to replace it. I haven't kept up on this in the past, 7 years? I haven't kept up on this in a few years now. So there might be the next cool thing. There might be some attacks on AES. I'm not aware of any, but like I said, I haven't been keeping too close an eye on it either. But AES is an algorithm that works very similar to, I shouldn't say that. If anybody knows what they're talking about, they're going to hate me for saying that. But somewhat similar to SHA-256, in that it's going to be a lot of bitwise operations and a lot of cycles through the encryption process. So you take the key and the message you want to encrypt, and you throw it through all these bitwise operations, take the output, and funnel it through multiple times to be able to get the hash, and not the hash, the crypto text, and then do it again with the same, throw in the decrypt with the same key to be able to decrypt the thing. Okay, so we can agree on a symmetric encryption key in a secure way. So let's talk about TLS itself. Let's get back to TLS at the high level. And how the TLS handshake goes, we need a handshake to do this key exchange. So first we have the client hello. Somebody wants to connect to a website. One of the first things your browser does is say, hi. Hi, server. How you doing? And you're going to send, your browser's going to send the algorithms that it supports, that it has implemented. Here are all the algorithms that I can use. Server's going to send its hello in response, which is going to say, here are the algorithms we're going to use. So the server is going to look at the available algorithms that the client supports. It's going to pick its favorite one and then say, this is the one we're using. Or if it doesn't support any of those, or the browser's really outdated and gave you a bunch of out-of-date, broken algorithms, the server's just going to say, no, we can't talk. We can't be friends. Update your algorithms. So as long as there is a valid algorithm here that the server accepts, it's going to pick its favorite one and say, this is the one we'll use. Server's going to send its certificate, which is signed by CA, so we can send that over. Notice none of this can be encrypted. None of this is going to be encrypted, but the certificate is signed, so we can verify that that certificate is good. Client and server go through this key exchange. When the server sends G to the A mod P, when the server sends its part, didn't I say the server was B? Yeah, the server computes G to the B. When the server sends G to the B mod P, when the server sends its portion of the symmetric key during this exchange, it will sign it with its private key. The server signs its portion of the symmetric encryption key with its private key, the one from its certificate that was sent right here. Then they go through with the rest of the key exchange. Now they agree on a symmetric encryption key, and then for that connection, and that connection only, they're going to use that symmetric encryption key to communicate back and forth in an encrypted way. So all of that, so after all that, we got TLS set up. That's the TLS handshake. And then we have HTTPS. So we reached our end goal. We're going to use that symmetric encryption key to encrypt our traffic. That whole process that we did there, so we generated the certificate. We had this public-private key pair. We sent the certificate to a CA, which has its certificate signed by a root CA. It signed our certificate, issued a certificate to us. We send that certificate to verify that this is our public key, this is our actual public key. During that whole key exchange, that public-private key pair, that whole crypto system we talked about last time, the certificate authorities, all of this infrastructure, all of this math, all of this stuff was to sign one piece of information. It was used to sign the server's portion of the symmetric key, and it wasn't even used for encryption at all. It's not even used for encryption during the key exchange. It's used to sign one value. That's it. That's the only reason we did all of that. Public key encryption and certificates, certificate authorities, root certificate authorities, all of it. Sign one value. And then everything happens with the symmetric encryption key. Now, one big reason for this is that public key encryption, it's slow. It's really slow. So we don't want to actually communicate. Even if we did bother having users generate their public-private key pairs and then encrypt it that way, it's really slow. So we don't really want to do that anyway. Symmetric encryption is much, much faster. AES is very blazingly fast. Public key encryption, very, very slow. And this also gives us, the way we're generating keys like this, gives us something called forward secrecy. So since a different key, well, actually not since, but a different key is generated for every TLS connection. Even if you're connecting to the same server, you're not going to reuse a key. You generate a new key every time. But since we're generating keys like this, we get something called forward secrecy. This is a very nice thing. So if we weren't doing this, say we were just using public key encryption to encrypt everything, and an eavesdropper spies on your communication, it's all encrypted, but they're going to log everything. They're going to remember every piece of conversation that you had between a server and every connection that that server had with every other user. It just stores all of that, just hoping that they're going to get the private key someday. And then someday they finally hit pay dirt, they attack the server, they get the private encryption key, and they want to decrypt all of this backlog of messages that they've been storing. They might be able to do that if we're just using public key encryption. But since we're negotiating this this symmetric encryption key, this session key, they can't even do anything. Even if they store all that traffic and get the private key for the server, they still can't decrypt that. They can't do anything because they'll never know, even if the server was logging their secret. Actually, no, that would break it, wouldn't it? Because they're never going to know A and B. They're never going to get A and B from the client and server because those were thrown away after that session. Nobody's going to store those values. So even with that, the attacker can't decrypt anything even after getting the private key of the server. So this is nice. This is big, nice, strong crypto properties that we have for this, which is what we want. We rely on encryption to keep us private on the internet. We want some nice, strong properties. So if an attacker does get a server's private key, they can only attack future messages they can only attack future messages that are sent after the fact. And even then, they have to launch a man-in-the-middle attack because when the server sends their portion of the symmetric key, they have to change that and then re-sign it with that private key to get their message sent. So not much that they can do, even with the private key associated with that certificate. We really took away a lot of their power with the way things are set up. How much computational intensity overhead does this add to communication after the symmetric key is established? I don't have a solid number for you. I don't have a solid answer for that. Non-zero for sure, but I'm not 100% sure. One thing I am prepared to answer is the network traffic. Think of the implications of this. You want to connect to a server, and you just want to get one piece of information. You just want anything from it. You just want their homepage HTML, maybe. Maybe that's all you want. What goes into that? Let's piece everything together and think about what happens during that. So one, we send the, can I remember them all? So the very first thing we have to do is send our TCP sync. So we send we send the TCP SYN, we get the ACK, and then we send our ACK and our request back. We get the server SYN. I should have just said the three-way handshake. So we have a TCP three-way handshake. We have a back, a forth, and a back to be able to just establish TCP. Then when we send, we can double up a little bit. On that last back, on the third leg of the three-way handshake, we can send our client hello for the TLS handshake, go through the TLS handshake. I'm just going to cheat and look at it on my slide. We're going to send the hello. The server sends a hello back with its, and it could send the certificate in the same message. It could send the certificate right away. And then we're both going to exchange our portions of our secret for the encryption key. And then we're going to compute that encryption key, encrypt a message, and then say, can I have your home page? And then the server can send back the home page. So we have, I lost count now, because we can double up a couple of them, but it's one for the TLS handshake, one for the hello, one for the key exchange, and then we can send a request. I lost count again. Was that 4? 4 round trips from client to server before we can do anything. Just to send one HTTP request, it's 4 round trips. So when you're connecting to a server that's, especially when it's located like physically very far away, you get quite a bit of overhead just in the number of round trips that it takes to establish the connection before any communication, before any especially encrypted communication can even occur. With just TCP and unencrypted, there's 1 extra round trip, but now we have 3 extra round trips to be able to do anything on the internet. So there is some overhead. There is cost to this, especially if your network's slow. That's if your ping is high, that's a lot. Yeah, and definitely cheaper than public key encryption. Yeah, probably not significant compared to the network. The network delays I just mentioned are going to be more overhead than the computation in most cases, I would guess. There might be cases where I'm wrong with that. Okay, so that's TLS. Oh, and I mentioned this. I got too excited and mentioned this in in Monday's lecture, I believe. But even when we're encrypting, everything's encrypted, and at the beginning of this lecture, didn't I? Even though everything's encrypted on the HTTP side, nothing's encrypted on the TCP/IP side. So somebody monitoring your traffic can still see who you're talking to. They can see what ports you're using, if that's interesting to them. But more importantly, they can see the IP addresses, your IP address and the destination IP address of all of the messages you're sending and receiving. So they can still see who you're talking to. They just can't see what you're saying. So this is why we still use VPNs in current year. Without VPNs, with VPNs, we can be more private. They can still see your IP address, but big deal, they can't see the other end. They just see that the other end is a VPN, which gives them much less information. Even that's not perfect. One, you have to trust your VPN, because guess what? They know everything you're doing. And two, I didn't have a second thought, but I wanted to say two. I guess two is they can still see that you're talking to a VPN, so their suspicion is going to rise, and then they're going to try harder to see what you're doing. Like if somebody sees you're connecting to YouTube, like nobody's going to care. But if they see you're connecting to a VPN, even if you're on YouTube, it's going to pique their interest if they're monitoring your traffic. Okay, and finally, self-signed certificates. So I mentioned these earlier, but this is actually what you're going to use for AO3 on the homework. So let's talk about what self-signed certificates are, and more importantly, how to generate them. So we would like to get a certificate, a valid certificate signed by a certificate authority. Like, why wouldn't you? Why wouldn't you want to do that? Well, nobody's going to sign a certificate for localhost. Doesn't make sense. Nobody's going to sign a certificate for localhost and say, you own localhost. You own that domain. Not going to happen. Doesn't make sense. So it's not really an option in our testing environments. When you go to deploy, get a domain name and everything, they'll sign it for that domain name and verify that you own that. Nobody's going to sign localhost. So for our testing purposes, we're going to use self-signed certificates, because I don't want to make all of you deploy just for testing. That everything would be wrong with that. So we're going to generate our own self-signed certificates for dev purposes. For that, we're going to use OpenSSL. So remember, SSL is just TLS. TLS is the new name, but they didn't update the name of the library, and I don't blame them at all for not changing it. Why would the name of the library change? Just because why would the protocol change names even? This is written in C, but there are wrappers in pretty much any major language. I say pretty much, but any major language, pretty much any language at all, to interact with it, including Python, JavaScript, Java, any of the ones that are being used by any of you in this semester. So find your OpenSSL library, install it in your code, or use the command line. You don't even have to install this in your code. We can do everything offline with this outside of your project, everything that we need OpenSSL for. So my recommended preferred way to use OpenSSL to generate a self-signed certificate is to install OpenSSL. If you're on Windows, you have to do this step because Windows doesn't make anything easy. If you're on a Linux or any Unix-based machine, it'll be already installed. You can just start using it. And run this command in your command line. And then it'll generate your self-signed certificate for you. Once you have your self-signed certificate, we'll see how to integrate that with Nginx. That'll be next time. But right now, I just want to talk about this command itself. that will generate our self-signed certs. When you run this command, you're going to be asked a bunch of questions. So when you do run this, like you could run this right now. Open your terminal and run it. It's going to ask you a bunch of questions. For most of them, you can just leave them blank. You just hit enter, and the default answer will be blank. But do not skip country code. You have to add your country code. This is a 2-digit country code. So for you physically being located in this room would be US, would be the country code for this location right here. So when it asks for country code, US, everything else, just skip it, and that's fine. Or if you want to add all your information, knock yourself out, that's fine too. So that's the practical side of this. But let's crack this open and talk about what this actually means, what all these parameters mean for this command. Because we're invoking SSL, OpenSSL, and we have all of these command line parameters. Let's go by these one at a time. We should be able to get through this today. Rec means give me a certificate. Dash X509, so give me a certificate with the X509 format, which is the standard format for certificates on the internet. Give me an X509 certificate. I want a new key using the RSA algorithm, and give me a 4K key size. Save my private key in a file named private.key. Save my self-signed cert in a file named cert.pem. This cert should expire in 1 year. Did I miss one here? Use the SHA-256 hashing algorithm for the hash for the hash of this certificate. And then no DES, don't require a password to be able to access this certificate. You don't want to be prompted for a password every time you want to use it. And that's it. Kind of boring, but that's all what all those command line parameters mean. So we could generate our certificates, install them right in our code, like I mentioned before. But what we're going to use is a reverse proxy server, and that's what we'll talk about on Friday. But you should never trust. So self-signed certificates, good for development. You should never trust these. If you're on the internet and your browser says, hey, this is a self-signed cert,